Hey, this is Steven from the Green Engineers, and welcome to another material comparison video. So today we're going to be talking about something that I was gifted at Tech Shop, a small little 40-gram sample, and it's of the filament called Iglide 180PF from a company called Igus. Igus makes plastic composite bearings and bushings. So they make a plastic composite low friction mechanical pieces that will substitute for metal bearings and such. So if you go to Igus's homepage and you look at the products that they have, or you hit home here, they have cable chains, they have self-aligning bearings for shoulder joints and stuff like that, plastic bushings, which is Iglide, which is what we're going to be looking at, dry line drive technology, dry linear guides, lead screw drive, lead screws, that's cool, rings, plastic ball bearings, Iglider again, bar stock, piston rings, all good stuff. Very good stuff. So, that being said, now I'm actually kind of interested in the piston rings. Anyways, so we're looking specifically at, most of that stuff is injection molded to your part to look, you build a mold and then you inject the polymer into the mold and you get your part. Here, they've just created something for the maker. It's been out for a long time, like 2014, 2013 it came out. And it's for printing your own, designing your own bushings and bearings and sleeves and stuff, and printing your own model, and then using it on your machines. So it's called the Iglide Tribo filament, and if you're not familiar with Tribo, I googled it. It's the study of friction, wear, lubrication, designs of bearings, the science of interactive surfaces in relative motion. So basically what that means is that it's a low friction polymer, or low friction filament. So that's why they call it tribo filament, is that if you look at it, you're like, Iglide tribo filament, like what is that? So if you knew what tribo was, you could basically assume that it's a low friction filament. So here it says new materials up to 50 times more abrasive resistant than conventional 3D printing materials. And they will prove that later on down the line. So they have a few, they have a few different types. They have the Iglide 180PF, which is the one I have a sample of, which it says here, to pick up a sample. 25 grams sample. They have the 170PF, and let's talk a little bit about them. They're excellent wear behavior, and most of the time when you print these, you're going to be printing at 220 to 250C, bed 110C, yeah. So generally around here, this one's giving in Fahrenheit, you'll probably be more familiar more with Celsius. So excellent wear behavior, most of them do have that. Hard to process, outstanding wear behavior of the tribo filaments. Then you have good resistance media, the J260PF, nozzle temperature quite a bit higher. So this one's like an additional 54 Fahrenheit, which is like 10 to 20 Celsius increase. So this one might be harder to do. Bed temperature also very hot, probably not going to be able to hit that with most beds, 266. Great wear resistance, especially when combined with plastic shafts, higher service temperature that you could run it in. So those are the, those are the few that they have. They have three, like I said, I have the 180, and this one I believe is the newer one. Okay, so there's a few, I was not able to find the actual mechanical properties, so, our standard, well, I found two here on this page. was not able to find maximum strain. It was also not able to find the stiffness. But on this page, you can see that the flexural modulus is 1,000 megapascals, and the flexural strength is 44 megapascals. So if you guys were here from my last video from Tallman 3D, their nylon lineup of filaments, this one falls between PCTPE and nylon 645. It's almost got the same properties here as nylon 645. And also that I was not able to find a comparison between this and nylon. So I'm not completely sure how well this is more smoother than nylon, lower wear resistance. But I'm thinking that this is some sort of nylon. It's probably some sort of type of nylon. Okay, so this is what we're looking for. Now what we're going to do is we're going to talk about the main thing that we're going to be talking about in this video, which is the wear resistance of this polymer compared to other popular 3D printing materials. So first thing we're going to check out is this graph to the left, and we see that we have a few specs that we're looking at before we look at the graph. So wear is linear, so basically what you have is what Igus makes is they make bushings that you put on rods or ball bearings or anything like that. So you'd have something like a 3D printer application where you would have a linear rod, like a chromoly rod, and then you would have a conventional ball bearing on here, right, normally. So you'd have a hard sleeve with ball bearings inside that would ride up and down on the shaft. Make a lot of noise, and also because they're similar steels, ball bearings are probably harder than the other steel, or vice versa, one's going to wear out the other. This one is a substitute for that material. So you would take off your metal your metal ball bearing and put on this guy. And the reason why the Iglide works like that is because similar to nylon, it has a very good self-lubricating property. So you also don't need to put grease down or anything like that. So as it slides up and down on the rod, it will lubricate the rod with its actual material. So basically what that would look like is it's like a sleeve, and it's got little fingers inside the sleeve, and the fingers, grab onto the rod at all angles. And as it goes up and down, the sleeves rub and leave lubrication, and that thus when it goes back through, it has very low chance of abrasing and removing material. So this is giving us the specs of the piece. So this is generally what this is like a sleeve, and this is like a this is like a rotation, like a ball bearing, like a bearing. So we have a velocity of 1 meter per second, a applied pressure of 1 megapascal, which is 10 times atmospheric pressure, or 10 times standard atmosphere. So that would be 140 psi, somewhere around there, which is pretty high. And then this is travel. This is actually lowercase l, I believe. 5 millimeter travel. So basically what it's doing is they have a test where they're oscillating, which I believe I have, yeah. So something like this, right? So they're oscillating 5 millimeters back and forth, right? Yeah, there's the bearing. There's the bushing. There's a bushing, and there's another piece inside the bushing. So that's the linear test. You're on this one. So that's the test, just back and forth over and over and over again. So maximum travel, 5 millimeters back and forth over and over and over again. So here we have the Y is the rate of wear, and this is picometers, so 10 to the 6th. Yeah, sorry, micrometers. Picometers 10 to the negative 12. Micrometers 10 to the negative 6 meters. So basically what this is saying is
for every 10 to the negative 6 meters of travel, for every kilometer of travel.
So a kilometer is 1,000 meters, and each meter is about 3.3 feet, I believe. So that's 3,300 feet. So it's like 2/3 of a mile. So for every 2/3 of a mile, the shaft will wear 10 to the negative 6 meters inwards, right? So if you have that that sleeve going up and down, every kilometer it will wear 10 to the negative 6 times whatever number it's on this graph. So for example, here PLA, it's at 400. So for every kilometer, or 3,000 feet, 3,300 feet, it's going to wear one micrometer, which is 10 to the negative 6 meters.
So there are two things here. Is you have the CF53 and the V2A. Those two are chromoly steels, or rust-proof steels. So those are steels used for linear rods, pretty much. Those are two different steels, so they're two different tests with the different steels that they're writing on. So basically what that means, what I believe this means, is that that's the steel rod, and then you have a bushing that's riding on that particular steel, those two different steels that they test. So CF53 is the orange, and the brown is the V2A. Okay, so PLA, which is one of our hardest materials, as we see here, 400 micrometers per every kilometer. So basically, it depends on what you're trying to achieve, how long you're trying to get to last. If you're thinking, okay, well, I'm using on 3D printer and we work in millimeters, so let's say I don't want it to be in the millimeter range, right? So if I'm a millimeter off, I'm starting to lose precision, and then I need to swap out the bushing. So in that case, we have 10 to negative 6, and so we'll move this over. We'll just say this is like off the graph, but let's just say it's 400. So we move over 1, 2. So now we have 10 to the negative 4, and for millimeters we need 10 to the negative 3. So let's say that this times 3, that's 1 millimeter. So that basically is saying that we could go 3 kilometers before we have 1 millimeter of wear. And then of course that's 1 millimeter on one side. So if you have a cylindrical bushing, so you have half on one side, half on the other side. So this is the diameter change. This is the total diameter change is 1 millimeter. So 0.5 on one side, 0.5 on the other side. But that's out of our specs. In this case, we don't want it past 1 millimeter. So it'll go a total of 3 kilometers before you have 1 millimeter of wear, which is not very far. That's 10,000 feet, especially if you have So let's just say 10,000 feet. In each print, let's just say you have a half foot. Let's just say you have a half foot build length. So let's just say that's a 3D printer. It's 6 inches of length, right? Which is half a foot, 12 inches per foot. That's a total of 20,000 travels back and forth. So that's not quite a bit, especially on a 3D printer where you're doing a lot, So 20,000 travels. Oops. Closed. So let's look at ABS. And so of course on this graph, the lower it is on the graph, the better off you are on the wear. So you want to be towards the bottom. ABS, we're looking at 95. So 95 compared to 40, so this was 3. So this was 3 kilometers. And then this is divided by 4, so that is 12. So a little bit over 12 kilometers on the CF 53, and this one is higher on the V2A steel. So instead of 3, that is 2.5, so that's 7.5, around 7.5 kilometers. So let's say that if you use the CF53, so let's say that this is times 4 times. So that's 80,000 passes on a 6-inch rod. Quite very, very good. PC ABS combo, polycarbonate ABS, which I know my buddies over at Protopasta have a polycarbonate ABS mix. So here we're looking at even higher wear on the CF53, but I'm looking at more popular 3D printing materials. These are not as popular, these two, but these are the main ones, but we'll look at them anyways. This one quite a bit higher, this one really high, as you see. So apparently V2A not very supportive of the materials. It's very high, very high. And then here, polycarbonate, we see that on the CF53, they play very nicely, very low kinetic friction. We are looking at 29, which is so it should double that's 10. So it's like, what, 20? This is 30, so it's like 15 or something. So it's like 15 times. So instead of 20,000, so that's 300,000 passes. So that's more what we're talking about. So you see a difference between the PLA, which is 20,000 passes, and the polycarbonate, which is 300,000 passes. 300,000 complete movements. So right there, you know, the lifetime just goes through the roof. So basically the 3D printer is going to break or be obsolete before this bushing goes bad. Which is what you want. You want the machine to last until they don't use it anymore. Then we get, oh, I did it again. Put it back up. Then you have, of course, the V2A, which is off the chart. Now we have the 3D printed material, the Iglider, which is the 170 PF. I have the 180, the next one, as you can see is a little bit higher. So the 170 is the low friction in the linear. So that's probably the one that you want. And then the Iglider J series, which is, in this case, it's the molded one, not the 3D printed one. So it's molded. And we have 4. So this is 100 times, right? 100 times in this. So you're talking about 2 million passes compared to PLA, right? So no other plastic bushing is going to compare, no other plastic 3D printed bushing is going to compare to this, unless, you know, polycarbonate is going to get close, and polycarbonate ABS mix. It's kind of funny because it seems like the ABS messes up the polycarbonate as far as that's concerned. That's kind of weird. But yeah, so nothing that you're going to be able to 3D print is going to be able to compare with that 170, because that's 2 million passes compared to 20,000 passes. You know. And then if you use V2A, you know, that's even more. It's probably like 3 million passes. The 180 that I have is not nearly as good. So 400. It's 571,000 passes, so that's pretty good. So the Iglider has the Iglider 170 compared to the 180. This one has almost 4 times the wear resistance. And then here, this is twice. And then of course, as you see, molded is just like a fraction of that, very, very small. So it's 4 times 4 again, that's 16 times. So this is 16 times more wear resistant than this one. So incredibly wear resistant out of a 3D printed part, right? So this is insane, because the 170 and the 180 are designed for 3D printing, I believe. The J series is what they use internally. So those two are 3D printed materials, tested. Because I believe they don't make anything that they sell out of their store out of this. They make it out of the J series. So this is completely 3D printed, just whooping everything else as far as wear resistance goes. And then here we're looking at the wear pivot. Here's the pivot. So again, these are those little arms. Oh, here's the bushing in here. So there's the bushing. Let's look at it really quickly. PLA, low wear resistance and pivot, very interesting. And this is again per kilometer. Oh, I forgot to go over the test. So 0.01 meters per second. I'm pretty sure that this is angular speed. 1 Mega Pascal and 60 degrees of rotation, beta. I'm gonna assume that that's 60. I don't know why I didn't use that alpha theta, but use beta. 60. I'm gonna assume that that's just the 60 degree of rotation on that pivot test. All right, so we're looking at 63.9, 7.4 for PLA. Very, very good for PLA out of the bat. ABS, quite a bit higher. Where is it? Again, this is identical graph, as far as it's set up. V2A and CF53. ABS, quite a bit more wear resistance. Polycarbonate ABS, huge wear resistance on the CF53 material, lower. Polycarbonate, extremely low. And you see here, Iglider, not really going to beat out polycarbonate very well. So this is kind of where it seems to be falling on its face. But Iglider J is 8 times better than polycarbonate. But again, it's got the star, which means it's molded. So it's a molded plastic. So this is what Igus uses internally, but now they're starting to create this outside with the J series that we saw, the last filament at the bottom, the 260 or whatever it was. So I don't know if we're going to be able to get this type of performance, but these are the two we're looking at right now. 5, so just a little bit better, and then this is twice as good, and then this is 3 times as good as polycarbonate. So still very, very good. But where you're going to see the benefits is in the linear rather than the rotational. So the rotational is showing that you might as well go with PLA, because I've seen some things where PLA as gears have outlasted ABS's gears quite easily. So I'm seeing that here, and then way better. So this is what, 4 times. So it's 4 times less friction than ABS, and then this is of course against steel. Alright, so here, Iglider not as good, quite a bit better than PLA, and then of course polycarbonate and polycarbonate ABS mix are quite rare plastics. So it's very, very good. Alright, those are the main 2. I just want to show you guys some prints of what those particular ones would look like. So here's a bushing, like I said, with the little fingers, and then some mounting holes for bolts, and then a linear rod would go through there. And then here is the brim to keep the edges from lifting and add better adhesion to the bed. And you see both are printed with a brim. And then here, maybe like a belt. Maybe a belt goes in there, or something slides in and out, or something. But again, with a brim. Very, very nice print. And then here's a bigger version, expanded version. Oh, and then this is oscillation. So this is another one. ABS quite a bit higher than PLA. It's wear linear wear oscillation. So yeah, this is that other one that we're looking at. So same identical one. All right, so let's talk a little bit more. Yeah, so hardened chrome CF53, load 15 megapascals, swivel angle 60. So here's like some of their bushings. Oh, here we go. Yeah, so it says bending E modulus tensile strength. strength master. So yeah, it's not saying. Yeah, so they don't really tell you how much they flex. Anyways, so yeah, here's another one. So we'll go over just a few more tests. So here again, here's some more bushings. ABS bushing, Iglide 180, and Iglide J. And then this is molded. This is an actual printed one, and these are both printed. So here's a linear test, long stroke. Here's a linear test here, very long stroke. Surface pressure, 0.1, so this is basically atmospheric pressure. 100 kilopascal. Surface speed, 0.34 meters per second. Stroke is 0.370 millimeters, which is basically around a foot. It's around a foot. It should be around a foot, around 12 inches. Yeah, it's around 12. It's around a foot, so 12 inches. Aluminum duration it went for 3 weeks. All right, so let's go ahead and take a look. So here's A, which is the ABS versus the iGlide versus the iGlider J. So if you remember on that first one, on the linear wear test, the ABS beat out the iGlider. I mean, not the iGlider, the PLA. So that's why they're testing this. So wear rate again is in micrometers of wear for every kilometer. So we're looking at 13.3 compared to the 3D printed iGlide 180 PF, which is again the sample that I have here, the free sample, and that is 0.8. So that, what was that, 40 times? So 40 plus times less wear than the ABS bushing. And the iGlider J, which is molded, which is another 4, so that's like 170 times less wear. So wow, 140 times less wear. Sorry, 40 times. 40 times less wear for a 3D printed part. And then here's more of what I was looking for. Gear wheels from Dynamic Tests. By a factor of 15. Did I do that wrong? Why did I say 40? Anyways, I don't know why I said 40 is 12, and then so this is times 4, so that's... Anyways, so I'll look more here, because I was way off on that math. I'm probably off in a whole bunch of parts here on my math, but you guys can do the math as well. I'm just trying to do it in my head. Okay, ABS standard material considering wear when subject to a torque of 1.2 Newton meter over an operating time of 75 hours. In contrast to this, the printed iGlide 180B gear wheel shows hardly any wear, and although subjected to a higher load over a longer period of time. Okay, so again, I wanted to go back to this. This is over 3 weeks, so you can calculate, how many kilometers that is, but that's crazy. So this is probably, you're talking about 13.3, 10 to the negative 6, 10 to the negative 5, 10 to the negative 4. So that's 0.13 millimeters. Yeah. It's 0.13 millimeters. So yeah, that's that's getting up there. So it would have to go quite a bit more kilometers. Okay. Yeah. So unfortunately here it shows that it shows the wear between the two. You see that these are starting to kind of starting to narrow and starting to have like this dip here. These are definitely starting to narrow compared to these. So you see that these are the wear is very low. So very low wear for gear So, which is more of what I'm looking for. So that's what I'm looking for. And then this was 1.2 Newton meters of torque over an operating time of 75 hours. So that's pretty good. So this is kind of the application that I'm looking for. So great for gears, stronger than ABS. But would it be more wear resistant to PLA is the question. Alright, so here's the standard linear test that we went over. 1 megapascal surface speed, 0.1 meters per second. Stroke 5 millimeters 1 week. Shaft CSS CF53 and V2A. ABS, Iglide 180 printed, Iglide 170 printed, Iglide J260 printed, and then Iglide J260 injection molded. So here's where we could actually get a comparison between the 260 injection molded and 260 J260 printed. Okay, so ABS up there, 50 micrometers per kilometer. So that's 0.5 millimeters per kilometer. Now we're looking at B, which is the Iglide 180, which is the one I have, and it's 6.9, which is 8. It's around, well, yeah, so it would be 7, because it's almost 7. So it's 7 times less wear resistance than, more wear resistance, sometimes more wear resistance than ABS. 3D printed, remember these are all printed on a 3D printer. And then this one is 10, a little bit over 10 times. And as you see, the V2A is dropping here. V2A is low. It prefers the V2A over the CF35. So this is over 10, over 10, over 20, around 20, and then this is again 20, and then this is 100. Wait, this is 2, so it's 25, and then 25 times 4 is 100. And here again, close to 100, 120 or so. Yeah, a little bit under 120, 115. So, wow, incredible. Right here, 0.5, 100 times more wear resistance out of a 3D printed bushing, linear bushing, that has 1 megapascal, which is 140 psi, or 10 times atmospheric pressure on this part, and traveling 1 week, 5 millimeters. So you'd have to travel 100 times the distance to get the same wear compared to ABS, which is, ABS is way better than PLA in the linear test. So this is like one of the better ones in the linear test. So pretty crazy. Swivel test, and let's see the linear test here, the wear rates. So it's saying here that the Iglide J version of the filament is almost exact to the to it being made the traditional way. Obviously not. I mean, here this is like more than double the wear resistance between here and here, but obviously more than double the price that it takes to manufacture it that way. So crazy that you could print a part and have it this compared to ABS. I don't know if you want to think about it compared here, but just to ABS, crazy. Alright, swivel test, we went over this, but here they have the J260 printed again. So here's ABS printed for the swivel, and here we have again 140 psi and 0.01 meters per second and 60 degree pivot, 4 weeks on 2 different shaft materials. We have ABS at 100, B, which is the Iglide 180, which is the one I have too, so that's 50 times the wear. 5, this is 20, so here actually the 170 is higher. It's kind of weird. in both. This one's a little bit lower than that, but yeah, this is higher, quite a bit higher. So that's interesting. But yeah, what did I say? This was 4. So this is actually 25. 25 times more air resistance. And then this is 20. This is 50. And then this is, it should be like 75 or something. Anyways, so almost identical here between a molded part and a printed part. And then here, quite good. Alright, swivel testing, 20 Mega Pascals. So another one, but even higher pressure. So this is 1,400 pounds. Sorry, plus double. So this is 140, and then this is 1,400 plus 2, so it's 2,800. So 2,800 psi. Injection molded quite a bit higher. Yeah, up to 50 times higher than the standard 3D printed material. So Iglide 180, and this is not even ABS, because ABS probably break at that pressure. Okay, so here 40, so this is just like showing them comparison. And they see that the E, so similar. Alright, friction test, rotating, this is the last one. Coefficient of friction, ABS, B, Iglide 180, 170, J260 printed, and J260 injection molded. So we see here 0.53, 0.24, so double the wear resistance, a little bit over double, a little less than 4, and it's actually higher here. So 0.3, 1 time 2 hours. So this is just wearing. This is just like wearing something over it. So like you lock the shaft and then have it just run over it. So even just having something roll over it, not in rotating or anything, you see that it has still quite a bit of low friction as it's lubricating the pieces. So very cool. So yeah, that's basically it. Here's a few more tests. Here's the friction. Yeah, so it's just running a wire past, and then you have a tensioner there. And it's just running a wire past the pieces. Rotational. It's just rotating in a bearing, and the bushing being in there, beating on. Okay, so let's go ahead and talk really quickly about price. So here, as you see from Matter Hackers, Igus Iglide 180 PF Tribo Filament 1.75, and it is a 1/4 kilogram spool, $85. So a total spool is $350, around $350 for a full kilogram spool. So you better be, making quite a bit on selling this stuff. So let's go on to looking at the actual individual costs on Igus website. So we're looking at 250 grams, 59, 750 grams is 92. So obviously the good deal is to get the near kilogram, that's $92, which is additional $30, and you get 3 times, for additional $30 you get 3 times the weight. So that's pretty good. So and then this is the 180 that I have, and I got a free sample. So if you want a free sample, sign up for one at Igus and get them to send a 180, I believe the 180, the 170 also has that, and also the J has that. So go ahead and just pick up some samples from them, test them out, and see if they're gonna fit what you're looking for. And they're 25 gram samples. I thought mine was 40. It might be because of the package. I haven't taken it out of the package yet. 250, 750, 750. This is actually kind of high. Anyways, we'll talk about that in a second. So here, 750 is again 92. So you could get, and then here 94. So the 170 in most tests is quite a bit better than the 180, and you get it for an extra $2. So here in this case, so on that other website it is $350 for a full spool. Here it's, if you add these two, it's $150, but here it's just a little more. It's like probably $125, $125 for a kilogram, $125 per kilogram. And here actually, well here this one's quite a bit more expensive, the J260, but it has the two different sizes here for a sample. The the 170 actually is only available at 1.75. So here, 250 for $64. So 4 times that is 200. So about $250 a kilogram for the very, very low wear resistance of the J260. All right, so that's pretty much it for this video. I'm going to be testing out this Iglider 180 PF, and then see how that works. And I will be posting a video on that when I get around to doing that. But as you can see, very low friction, high wear resistance polymer from Igus for your 3D printer. And generally, as they say from Igus, if your 3D printer is able to print ABS and able to hit those temperatures, you shouldn't have any problem being able to print it and making custom bearings or bushings. Bearings or bushings or gears, or as you saw, wheel gears. Go on to their website. They have a whole bunch of CAD examples, 3D CAD examples of different things that you can design and whatnot. I will be testing this for the gear bearing and then seeing how that works compared to the nylons from Tolman and also PLA. Alright, well that's pretty much it for this video. Go ahead and check that out and pick up some samples and see how they work. And let me know how it goes in the comments. And I will catch you guys in the next video. Thank you guys for watching. Take it easy.